Hey guys, today we are taking a look at 3.1 functions for our notes. Yesterday in class you guys worked on the Desmos activity that explored kind of input-output relationship. All of those were based on a table. Today we're going to take a deeper dive into some vocabulary and looking at some of those other representations that we could be presented for a function. So first things first, just kind of giving ourselves some quick reminders here. A function is like a machine. You put something into the machine, you get something back out of the machine. What those two things are, our inputs and our outputs, are related in some way. We'll focus on specifically how they're related to at a later date. In later sections, we'll talk about how things can be related to each other and the relationships between those two. But for right now, all we're caring about is that there is a relationship between those two things. So our next little section down here, Our next section here, we're going to take a look at a couple of examples of functions and how they relate to each other in terms of our inputs and our outputs. Now we know when we depend on something else, our dependent variable would be our output. So our output always depends on that input. So the way they're written here, it's phrased as is a function of, really means the same thing as depends on. So in this case, the way our sentences are structured here, the first thing would be our output, which kind of seems counterintuitive, but this first thing depends on the second thing. So in our first example here, the length of my shadow is a function of the time of day, where in this case, my time is going to be the input, what time it is, determines the length of my shadow. Length of shadow. For the second example here, the cost of an airplane ticket is a function of the distance of your destination. So here again, your distance away determines the cost of that ticket, right? You fly to Paris, it's going to be more expensive than just flying from Chicago to Cleveland. And the last one, the number of students in a school is a function of the number of houses in the school district. Not exactly a perfect relationship going back and forth between the two, but there is definitely a relationship between number of houses and number of students. Because the more houses you have, the more potential you have to have more students. Next down here are some counterexamples, some non-examples of functions. So the following things are not related to each other. The size of your shoe is a function of the length of your hair. That's not true, right? Hair has nothing to do with the length of your shoe. If you grow your hair longer, your foot's not going to grow bigger. You need to wear bigger shoes. Those two things are not related to each other. But what we could say is, if we wanted to try and fix these, my shoe size is a function of the length of your foot. Would be one example we could use. Maybe you could say the shoe size is a function of the height of you. There's some kind of correlation between those two, where usually the taller you are, the bigger your shoe is, or the bigger your foot is, so therefore the bigger your shoe is. But really the length or the size of your foot is what determines that length or the size of your shoe. The cost of your grocery bill is a function of how far away the grocery store is. Again, not the case. I could drive all the way to Milwaukee and pay $30 for groceries, and I could just drive right up to Lake Geneva and pay $200 in groceries. It's not about how far we go away, it's how much we buy. Oops, I can't spell. How much we buy, how many groceries we get, how many food items we get, or maybe you could even say the number of people in your family. But even that again is not perfectly, related to each other. Where you could have a really big family that doesn't eat a whole lot versus a small family that eats a bunch. Last one, the color of my hair is a function of my height. Again, height has nothing to do with determining hair color. A perfect example of this would be dyeing your hair. Obviously those two things have nothing to do with each other, but the color of your hair could be a function of your genetics, your genes, or it could be of the color dye that you used. I know plenty of people dye their hair. The color of your hair is obviously determined by either your genetics or the color of your hair dye that you choose. All right, for this next section, we're getting into the more mathematical definition of what a function is. So here, a function is a special relationship where each input has a single output. meaning every time I put a number into my function, I get the same output back out. This we call, I'm going to write it in a different color, we call a one-to-one, whoops, I'll write it in words, a one-to-one relationship, meaning one input has one output, one-to-one. Functions relate each other, functions relate each number of a set with exactly one number of another set. Meaning we could have more than just a single number being put into our machine and then going back out. We're taking that number that we're putting into our machine from a set of numbers, and we're going to go ahead and have that correlate to an output from that other set. Again, that's just exploring that idea of being one-to-one, but talking about it in terms of sets. Now, the list below, we have a bunch of different representations that we can be given a function in. We've seen 2 of them so far. On the previous page, we saw functions represented using words. And our table, the second one down, is what we saw yesterday in our Desmos activity, where I list all of my inputs and outputs in a data table, and that's how we're comparing those things. We also have 3 other sets of representation, 3 other types of representations. We could be given them in webs, or what I call mappings. Sometimes people refer to them as little beans. We also could have just sets of points, so lists of coordinates. And then, of course, we also have graphs that will be one of our main focuses for this school year, is graphing things. The next section down here, the last one, non-examples, so things that are not functions. We do have a specific word that we use for that, and we just call that a relation. Or sometimes we would just call them non-functions. But usually I'll use the word relation, because there could still be a relationship between those 2 things. But again, if it's not that one-to-one relationship where my input always has the same output, we don't call that a function. We can just call it a relation. So there could still be a connection between our inputs and outputs, but if it's not one-to-one, it's not a function. So heading on down in our table here, we're looking at some of our different representations and how we can identify them, or what they look like when they are examples, which are functions, or when they're non-examples, so they are relations. So if we look at our table we looked at yesterday for our Desmos activity, where we saw functions versus not functions, again, we're looking for those times where our input goes to 2 different places. So what you want to key in on for our table is you're looking for spots where my x value repeats. So I have 2 of the same x values, my inputs, but they go to 2 different places. So in this non-example here, this 2 going to 6 and going to 8 is what tells me that this is not a function. So here for our rules, this is again, our rules is more so just reminders for ourselves. So here, does x always go to the same y value? If not, then it is not a function. All right, so in our tables, our inputs are always that left column, and our outputs were always that right column, x and y, right? Inputs are x's, outputs are y's. Now, when we get down to this next one, this is a brand new representation for us, most likely, unless you saw this last year with middle school math, with 8th grade math, which I don't think that's usually a common thing that you guys have seen. But this is what I call mappings. We're mapping one thing to another. Some people call them webs. Some people call them beans because they kind of look like these little, like, I don't know, the way I've drawn them before, they look like little beans. I usually call them mappings just because, again, it maps one thing to the other. Now, that same relationship where this left set is our inputs, our right set is our outputs. The way that we read this is everywhere we have an arrow that shows us a spot where our input goes to our output. So in this case, 8 goes to -1. That we have an input-output relationship. -5 goes to 0, 0 goes to 0, and then 2 goes to 2. So here we don't have any x values going to two different places. So again, this is another example of what a function would look like for a mapping in this case. Now, if we take a look at our non-example here, these ones to me are easiest to identify because we can see that this -5 has two different arrows coming off of it, meaning this input, this single x value, has two different y values. So that is super easy for us to key in on, that this right there, -5, is the reason that this is not a function. This is just a relation. So for our notes here again, kind of the same question we had before. Does x always go to the same y value? And here specifically, we're looking for input with two arrows. If we see an input that has two arrows coming off of it, then we know that that's not a function. That's just a relation. All right, moving along. Our graph. Now this one, if I said, I know I said mappings are the easiest one to see. For me personally, I actually prefer my graphs. They're just my bread and butter. I've spent a lot of time working on them. With our graphs, we're still looking to see if we have two x values that have the exact same y value. Now in a graph, we have this special test for it. We call it the vertical line test, or I will abbreviate it to just VLT. Now, vertical line test, because on a graph we know our left and right coordinates are our x values, our up and down coordinates are our y values. So that means if I'm looking for two of the same x values, that means they're both going to have the same vertical position, or sorry, the same horizontal position, meaning if I draw a vertical line, those 2 points have the same x value. So what I'm looking for is some examples of where that wouldn't be the case. If I have two of the same x value that have different y values, that would mean, so here, if you draw a vertical line that crosses the graph at more than 1 point, it fails vertical line test and is not a function. So the way we'll do this, we'll take a look at our graphs. If we can draw a vertical line somewhere on our graph where it crosses my graph function more than once, then it fails vertical line test and it is not a function. Here in this first one, you can see no matter where I draw my vertical line, anywhere on this first one, there aren't any spots where I cross more than once. And really the same thing happens here. Anywhere on this curved graph, I can draw vertical lines. Even though there are curves to it, there aren't any spots where I have my blue graph crossing my yellow lines more than once. But if you look at our non-examples here, because they're opening sideways or they've got some swoops to them, we can see we can draw my line. Now we want to draw an actual perfectly vertical line, but we can see here in this case I've got those two spots where my graph crosses that vertical line. Or even here at the y-axis, we can see right here and right here are another set where I have more than 1 point that crosses my y-axis, or my vertical line, which tells me that because I'm choosing a vertical line, I have the same x values, but then I'm getting two of those different y values. And again, that same thing happens on this kind of swoop-diddy equation here. If I draw a vertical line, even in here, I can get 3 different points, 1, 2, and 3. So that definitely fails vertical line test, meaning those two are just relations, not functions. Okay, for our last one, for our set of points, this one a little more tedious and time-consuming. It's basically the same thing as my table. It's just that they're listed as coordinates instead of left and right x and y values. So you're still going to be doing the same thing. You're still looking for anywhere you have the same x value, but with different y values. So it's just going to take a little bit more eye spying here for us. On my non-examples here, I can see that I have 2 different points. Because again, here, I guess if I didn't say that already, or in case you forgot, x comma y, input comma output is our structure for our coordinates. So here we can see for 13, it goes to 3 and it goes to -1. Here, 2 goes to 0 and to -4. So that's why it is not a function. So here I'm just going to write same as table. If you've got 2 x values that are the same but have different y values, that is not a function. Okay, for our last one, decide whether each set of data is a function. If it is not a function, indicate the part of the data that shows that it's not a function. So as we go through these, I'm just going to go through them pretty quickly. If you want to pause as we before I get started here and check yourself and see if you can figure out whether they're functions or not, then go ahead and do that. But I'm going to go ahead and now just go ahead and start working on these problems. Number 1 here is a function. I'm just going to say f. There's no inputs that go to 2 different outputs. Number 2, I can see here 2 goes 2 different places. So I'm going to say that's a relation, or you can say not a function, NF, if you want to use that. For number 3, -8 goes 2 different places. So again, not a function. For number 4, B goes 2 different places. So once again, not a function. For number 6, all of my inputs go to the same output every single time. So this one is a function. For number 6, we can see we've got a bunch of different examples on why this isn't a function. We see -6 goes 2 different places. We've got -5 goes 2 different places. -4 goes 2 different places. You've got 3 different choices on examples on why this is not a function. Okay. For number 7, vertical line test. We got a nice sideways parabola, which you'll know what those things mean eventually. So this is, once again, not a function. Number 8, same thing. I have a vertical line that I can draw in anywhere in that little bean-shaped thing to show that it crosses at more than one point. So 8 is not a function. However, number 9, because it's just a line that is at an angle here, I can draw as many little vertical lines as I want to. There's not any spot where it crosses more than once. So number 9 is a function. So we've got function, not a function, not a function. So actually, it's probably just easier to say. Number 1, 5, and 9 are functions. Everything else are not functions. All the other ones are not. So that's all I got for you guys today. Homework is on pages 108 and 109. You guys are doing 4 through 22, just the evens. So now that we're done watching the video, go ahead and get started on that for the rest of the class period. If and when you guys have questions, you can feel free to shoot me an email. I may or may not respond today, but if not, definitely have those questions ready to go when I'm back on Wednesday. All right, guys, have a good one, and I will see you guys tomorrow.